The title of this note is Solving Logarithmic Equations, and the outcome is that you will be able to solve both an exponential and a logarithmic equation. So there's 4 types. There's going to be 2 exponential and 2 logarithmic types. So first we're going to look at this exponential type. This is the simpler of the 2 types. You have a simple logarithmic equation when, if you look at the bases, so ignoring the exponent, 2 and 32. If you can rewrite the larger number, so in this example the 32, as a power of 2, that's when this is a simple equation. So that'll be your first step. You're going to rewrite both sides of the equation so they have the same base. You want to use the smaller number for the base. So in case you can't see that, it says 2 to the x minus 3 equals 32. So the smaller base is 2, so you're going to say, hey, 32 is the same thing as 2 to what power? So 2 squared is 4, to the 3rd power is 8, to the 4th power is 16, to the 5th power is 32. So you're going to rewrite the 32 as 2 to the 5th power. When both sides have the same base, they cancel out. So it's true that the exponents are the same. X minus 3 equals 2. Technically what's happening here is you're taking a logarithm. You don't have to write this, just so that you understand what's happening. You're taking the logarithm of both sides. So I'm just going to adjust this here. Still equals. I just slid it over so that I can write log base 2. And log base 2 of 2 is what is canceling out. That's equivalent to 1. That's how you're getting x minus 3 equals 5. And then from this point, you're going to solve for your variable. That's your step 3, solve for your variable. Remember, when you're solving, you're doing your reverse order of operations, which you might hear us call SADMAP. So I'm going to add 3 to both sides to get that x equals 8. So let's look at an additional practice problem. There's actually 2 problems here coming right out of page 386 from your textbook if you want to follow along there for an additional resource. So I see 5 to the 7 minus x equals 125. So the smaller of those 2 numbers is 5. So I'm going to ask myself, how can I rewrite 125 as 5 to some power? I'm just going to move that problem out of the way for now. So I know that 125 is 5 to the 3rd power. Once they have the same base, you can cancel out the bases and set the exponents equal to each other. That's called the one-to-one property. And now I'm solving for x. So negative x equals negative 4. Divide both sides by negative 1. X equals 4. One more practice problem. This is 1/2 to the 4y equals 16. So the smaller of the 2 bases is 1/2. So I'm going to ask myself, how can I rewrite 16 as 1/2 to some power? Well, I'm going to think about 2. 2 to what power makes 16? 2 to the 4th power. But the 2 is in the denominator, so I'm going to use my negative exponent property. If I want to move something to the other side of the fraction, I will use a negative exponent. 1/2 to the 4th power would be 1 over 16. But I want the reciprocal, so I'm going to use negative 4 to get the reciprocal of 1 over 16, which is 16. So I can rewrite 16 as 1/2 to the negative 4th power. Now that the bases are the same, I can use that one-to-one property to equate the exponents. And now I just have to solve for the variable. So I see that y equals negative 1. So those are the simple equations. The simple equations are when you can make 2 sides have the same base. Now we're going to look at the complicated equations. The complicated equations happens when it's impossible to make the 2 sides have the same base. So first you want to isolate your exponential expression. You're isolating using SADMAP. So you can see in this example here, first we've added 2 to both sides to get 9. Then we're dividing both sides by 3, and we have e to the 2x equals 3. So here's an example. There's no way we can write 3 as e to some power. So when this happens, you're going to take a logarithm on both sides. You want to use a logarithm with the same base. So because this is a base e, we're going to use a logarithm of base e, which is a natural log. So this is the natural log on both sides, and the natural log of e, sorry, I don't know how to move that, cancels out, which is why we just have 2x equals the natural log of 3. And then we're going to continue to simplify. So you're continuing to do SADMAP, dividing both sides by 2. And then remembering our properties, dividing by 2 is the same thing as multiplying by 1/2. So let's look at 2 practice problems. These are both from page 387 of your textbook. So the first one we're going to look at is 5 to the 3x equals 16. So again, it's not a simple problem because there's no way I can write 16 as 5 to some power. It's not going to be a nice number. So instead, I'm going to take the logarithm on both sides. I want to get rid of the 5 because I want to have 3x by itself on the left. So I'm going to get rid of it using a logarithm of base 5. And what I do to one side, I will do to the other. So the right side becomes logarithm base 5 of 16. In algebra, you can do whatever you want to an equation, as long as you're fair and consistent and do it on both sides. So log base 5 of 5 cancels out, and I have 3x equals log base 5 of 16. Now, here's something where I'm going to, if I wanted to approximate this, I could go to the calculator to get this value. You don't have a log base 5 button on your calculator, so you have to do what's called the change of base formula. Again, these are in your properties. You can find this in the calculator by doing log 16 divided by log 5. That's a change of base formula. You do log of the big number divided by log of the base. And then that'll give you a value in your calculator. The last step you would do is you would divide by 3. So whatever this number is, I'm going to divide it by 3. So if we want to see that, let me pull up my calculator here. So I want to do log of 16 divided by log of 5. Make sure you're closing those parentheses. And then that value I'm going to divide by 3. And if you're going to give a decimal answer, you need to approximate out to 3 decimal places. So 0.574 would be the approximation for x. All right, so let's look at another problem. This time, 4 to the 3x plus 2 equals 71. Again, we cannot write 71 as 4 to some power. So we're going to instead take the logarithm on both sides. We're going to take a log base 4 because it's that 4 we want to get rid of because we're trying to get x out of the exponent. Log base 4 of 4 cancels out. And then I want to finish solving for x doing SADMAP. I don't like to put things after the logarithm, so I'm just going to write -2 in front. And then my last step is to divide by 3. And again, I can go to my calculator to figure all of that out. So those are your exponential equations. So next we're going to look at logarithmic equations. So again, starting with the simple kind. What you want to do is you want to have a single logarithm on each side. That's your first step. So you can see here, when there's a plus sign, it gets combined with multiplication. So the left side becomes log x times x minus 3 equals log 4. When both sides have a log, the log gets canceled out. So then you have x times x minus 3 equals 4. That's that one-to-one property to equate the arguments. The argument, that's just a fancy word for the input. the input of the log function. And now you're using your algebra skills to solve. This needs to be distributed. And so you have x squared minus 3x equals 4. You notice it's quadratic, so you got to set it equal to 0 to factor it. And there's two solutions, -1 and 4. When you're dealing with logarithms, you do need to check your results because you will get extraneous solutions. You will have answers that you get algebraically but don't actually work. So if you go back and plug this in, you have, let's say you go back to plug in the -1, -1 minus 3 plus log of -1. -1 minus 3 is -4. Well, you can't take the log of negative numbers. The domain of a logarithmic function is values that are greater than 0. So you can't take the log of 0, can't take the log of a negative number. So -1 is an extraneous solution. We should check 4 as well. 4 minus 3 is 1, that's okay. And 4, you can take the log of any positive number, so that one will work. So the only solution is x equals 4. Okay, we're going to try a problem. This problem is worked out in your book on page 389. So I see the right side, I have two logarithms. I need to condense it into a single logarithm. Copy in the left side first. I see addition, so I can condense that with multiplication. And now that I have a log base 4 on both sides, I can just cancel it out from both sides. So 2x minus 3 equals x times x minus 2. I'm going to save myself a step here and distribute. So I see this thing is quadratic, so I'm going to go ahead and set it equal to 0. Now I can factor. I'm looking for two values that multiply to 3, add to -4. So that would be -3 and -1. So my solutions are +3, +1. My potential solutions, I should say, because I always want to go back and check. So I'm going to plug these values in. If I plug a 3 in, 2 times 3 is 6, minus 3 is 3. That's okay, because it's positive. 3, positive. 3 minus 2 is 1, positive. 3 works, because the arguments are all positive. Now let me plug 1 in. So 2 times 1 is 2, minus 3 is -1. Oops, can't take the log of a negative number. I don't even need to continue checking. 1 is an extraneous solution. So the only solution is 3. So that was the type where there was a log on both sides. We have one last type. This is the complicated log type, where you will not have a log on both sides. So first you combine and isolate the log expressions. You want to have a single log. And then you're going to rewrite it as an exponent using your front, back, middle, or whatever technique you like, the snail or the loggerroll, whatever makes sense to you. You're then going to solve for the variable, and again, check for extraneous solutions. So we can see in this problem, the minus sign turned into division. So log base 5, so to rewrite it as an exponent, we went front, back, middle. So that's why it's 5 squared equals the argument. Rewriting 5 squared is 25, multiplying both sides by x. X plus 2 equals 25x. Subtracting x from both sides, you get 2 equals 24x, and then dividing by 24. So one last practice problem. This one's from page 390 in your text. It's already simplified to a single log. That's so convenient. So we are going to solve for x. We want to get rid of that logarithm. It's a log base 3. I can do my front, back, middle, loggerroll, snail, whatever makes the most sense to me. What's really happening here is we're exponentiating. We're putting a base of 3. Because 3 to the log 3 cancels out, that's our property, equals 3 to the 4th. So however you get to exponential form, you're going to get to this step. And 3 to the 4th is 81. Now I want to multiply both sides by x minus 8 to get rid of that fraction. So 9x equals, actually I'm not going to distribute because I don't want to multiply 81 times 8. I can divide both sides by 9. And I see, kind of convenient, I can just do 81 divided by 9, save myself some intense distributing. So x equals 9 times x minus 8. You see the GCF of 9 there? So now I can distribute. And I see, I'm going to write it over here, 9x minus 8 equals x. I can add 8 on both sides. And then I can subtract x from both sides. 8x equals 8. I'm getting x equals 1. I should go back and check, make sure that the argument's positive. So if I do 9 times 1, I get 9, and 1 minus 8 is negative 7. 9 divided by negative 7 is a negative value, and I cannot take the log of a negative value, so this is not a solution. So it turns out that there are no solutions to this one. That is the end of these notes.